Hello, everybody. My name is Toma Lange. I'm a PhD student at the Technion. Today, I'm going to present a work of mine, which is joint with Professor Sefi Naor and Professor Gala Edgar. And our subject is offline and online algorithms for SSD management. A few words on SSDs and their limitations. SSDs support only out-of-place page writes. When we write a page, we should write it to a clean location. Its previous version becomes invalid. Cleanings are performed in block granularity, and upon cleaning, each valid page in the cleaned block must be rewritten to another clean location. Now, the issue is that such page rewrites are bad since they reduce the endurance of the SSD and harm its performance. When we think of an SSD, we can think of a table in which each column represents a block, each cell represents a physical page. Logical pages and physical pages are of the same capacity, and to avoid confusion between these two, from now on, instead of physical page, I will simply say a slot. So green cells represent valid slots, dotted cells represent invalid slots, and white cells represent clean slots. And assume for a moment that we want to write a page to this SSD. So we should write it to a clean location. For example, here, the previous version of that page becomes invalid. And now we want to clean this block, for example. So since it stores a valid page, we should first move it to a clean location. And now we can turn to clean that block. The contribution of this research is threefold. First, we formally define the SSD management problem. We address this problem from a theoretical perspective. In particular, we analyze algorithms in a worst-case fashion. Finally, we propose an efficient approach for reducing write amplification in SSDs, and this approach can be applied in both offline and online settings. When we think of algorithms for SSD management, we distinguish between two components. The victim selection determines which block to clean when, and the placement strategy determines where to write each page. Two classical algorithms are greedy and hot cold. The greedy algorithm always selects the mean valid block for cleaning. And regarding the placement strategy, it simply fills that block. Actually, it does not distinguish between different pages. Hot code is actually a family of algorithms that allocates different blocks for different page temperatures. And all of them apply greedy cleaning within each area. Okay. Regarding the performance of these algorithms, so it was shown that the greedy algorithm is optimal under uniform distribution. And however, hot code seems to perform better when the distribution is skewed, which commonly happen in realistic traces. In the first part of our work, we concern myopic algorithms, where a myopic algorithm is an algorithm that has no information about the future. We express our results using the spare factor, denoted by alpha, which is defined by the difference between physical and logical capacity over the physical capacity. And we have here three basic results. The first one states that for any request sequence, the write amplification of the greedy algorithm is not greater than 1 over alpha. The second result states that no deterministic algorithm can provide a better guarantee. That is, for any deterministic algorithm, we always can find a request sequence on which the write amplification of that algorithm is at least 1 over alpha. And the third result is that no randomized algorithm can provide guarantee better than 1/2 alpha. Okay, so now we turn to describe our approach. A key notion here is the death time. The death time of a page is simply the time it will be accessed next. So ideally, it was shown that each block should group pages with consecutive death times. This way, blocks are invalidated sequentially and no rewrites needed. Unfortunately, when the sequence is not sequential, we mostly cannot maintain such an optimal layout. So our approach is like this. We start with an optimal layout. We serve new requests while keeping the layout almost optimal. And when the layout becomes too far from being optimal, we reorder all pages. Okay, so now we turn to describe how we apply our technique in the offline setting. So we begin with the victim selection. So we clean blocks in general only when the SSD becomes full. That is, it does not contain any clean slots. So in this case, there are two options. If completely invalid blocks exist, that is, blocks that contain only invalid slots, then we clean all of them, okay? For example, here there are two completely invalid blocks, we clean both of them. Otherwise, if such blocks do not exist, then we reorder all pages, and we reorder them by the death times. For example, if this is the initial state, there is no block that is completely invalid, then we reorder all the pages such that each block groups pages with consecutive death times. Okay, what about the placement strategy? So after a cleaning step, we have a set of blocks which are all clean. That is, all their slots are clean. So in this case, we consider the next requests, in particular the death times of the next access pages, and we write the pages into the slots such that they are sorted by their death times. For example, if we have two clean blocks, 4 slots each, so we consider the next 8 access pages and we write them in a sorted manner in the clean slots. Regarding the performance of this algorithm, so we can show that for any request sequence, the right amplification is not greater than 1 plus O of 1/B, where B is the number of blocks in the SSD. This is a very efficient algorithm. And the key idea in the analysis is that the reordering steps are very rare. And note that this is the only place in which we perform page rewrites. A natural question is whether our algorithm is optimal. Consider for a moment the following decision problem in which we have a request sequence sigma as an input, and we ask whether sigma can be served without rewrites, that is, with right amplification which is equal to 1. It turns out that this is a special case of a graph problem named fragmented coloring on interval graphs, which is a generalization of standard vertex coloring. However, the computational status of this problem is open, and we also cannot determine whether our problem is NP-hard or not. And for now, we'll leave this question open. We now turn to augment the online setting such that we assume that each request arrives with a predicted death time. Our goal in the placement strategy is to sort pages by predicted death times. However, we tackle a problem here. Look at the figure below. Assume that we have 2 blocks, which we fill with the next access pages. And we already filled 6 pages with death times 1, 2, 3, 7, 8, and 9. And now a page with predicted death time 5 arrives. So actually, we do not know where to place it, since this decision depends on future requests. So we propose the following solution. We assume the availability of a small, fast additional memory. And when I say fast, I mean that we allow ourselves to neglect any implication concerning its management. So we use this memory as follows. Instead of writing pages to the SSD immediately, we first aggregate them in the memory. And as soon as the memory becomes full, we move the pages to the SSD, sorted by the predicted death times. Note that in practice, predictions might be erroneous. So we define the prediction error denoted by eta as the sum over all requests of the difference between real death time and the predicted death time. And note that in our placement strategy, we just believe predictions. The question is, what about the victim selection? In the victim selection strategy, we have two options. The first option is to consider predictions. For example, we can avoid cleaning a hot block. However, the problem is that in this case, large prediction errors can be disastrous. So in order to limit the effect of prediction errors, we choose the following option, in which we always clean mean valid blocks regardless of predictions. Okay, so now we turn to illustrate the operation of the proposed algorithm. We assume that initially the memory is empty and the SSD contains no clean slots. So in this case, the first step should be a cleaning operation. And we select mean valid blocks whose capacity is equal to that of the entire memory. So in this example, we select 2 mean valid blocks for cleaning. The mean valid blocks here are these blocks. So we choose them for cleaning. They store a valid page. So we retrieve this page back to the memory. Okay, now we turn to clean the victim blocks. And the next step is to serve the next requests until the memory becomes full. So let's serve the first request. The first page is written here. The corresponding slot becomes invalid. And this way, we continue until the memory becomes full. At this point, we write the pages stored in the memory to the SSD, and we do it such that the pages are sorted by their death times. Regarding the performance of this algorithm, we proved that for any request sequence, the right amplification of this algorithm, which is now given as a function of eta, is not greater than the minimum between 1 plus O of eta over t, which is the average prediction error, and 1 over alpha, which I remind you is exactly the right amplification guaranteed by the greedy algorithm, plus a negligible additive factor, which depends on the memory size. So our algorithm actually possesses 2 desired properties. First, its performance improves as the error decreases. And second, it is never worse than the greedy algorithm, which knows nothing about the future. So before we show the empirical evaluation of our algorithms, we present a simple optimization we implemented for the simulations, in which we simply use the memory also as a cache. Since cache writes are for free, if a requested page, if the previous version of a requested page is already in the memory, so we can simply overwrite it. So in this case, due to cache hits, note that right amplification may be smaller than 1. Okay, so experimental evaluation. So in the first experiment, we compare all 4 algorithms, greedy, hot, cold, online, and offline. All algorithms are equipped with a memory of size 1% of the entire SSD. Greedy and hot, cold use memory as a cache with LAU policy. And in this simulation, predictions are exact, okay? And hot, cold uses the predictions to determine the temperature of each page. We consider two traces here. One was taken from a uniform distribution and one was taken from a ZIF distribution. On the left, we can see the uniform distribution. We can see that both offline and online algorithms achieve right amplification, which is very close to 1. In contrast, both cold and greedy achieve much higher right amplification, which gets better and better as the spare factor increases, obviously. However, there is a significant gap between our algorithms and greedy and hot cold. In ZIF, the gap decreases. However, there is still an improvement. We can see here. And obviously, all algorithms perform, the performance of all algorithms is better in the ZIF case, mostly because the memory is very, very efficient as a cache in this case. In the next experiment, we use both exact and erroneous predictions. Predicted death times are distributed uniformly in the interval t and y of t, which is the real death time. Spare factor is fixed here, and various memory sizes. Note that the dotted bars represent erroneous traces. You can see that the online algorithm still outperforms hot cold even when prediction errors occur. However, the gap is much smaller now. You can find further details on the experiments, including real traces, in our full version paper. Conclusion. We presented a theoretical analysis of both existing and new algorithms. We presented new algorithms that group pages by their death times. And we actually start bridging the gap between systems and theory community. And we hope that our findings may motivate the theory community to address SSD-related design challenges which have been overlooked so far. That's it. Thank you for your attention. I'm here for any question. Bye-bye.